Hi everyone. If you've seen my other videos or articles about how the ECU calculates the amount of fuel that needs to be delivered, then you'll see that they all end up with a fuel mass to be delivered. Now that doesn't give us the milliseconds straight away, so this article video is all about how the ECU goes from fuel mass to fuel milliseconds, or in other words, how an injector works. Now, this actually used to be part of how I interviewed people for job applications, so I'll probably have to pick a different topic now. But anyway, let's talk about fuel injectors. Fuel injector for a low pressure EFI system, I'm not talking about direct injectors at the moment, but as used on pretty much every port injected engine, it's an electromechanical device. So it has mechanical properties and it has electrical properties as well. Often they're not all that well understood, which is a pity because no one part of it's all that complicated. Now in this description I'm going to be mentioning fuel pressure a lot, and when I talk about fuel pressure what I'm talking about is the differential fuel pressure across the injector. So the pressure in the fuel rail minus the pressure in the inlet manifold. If you have a manifold reference fuel pressure regulator, then this value should be pretty much constant. If you have a fixed pressure regulator, as in a lot of modern OEM systems, then the differential fuel pressure is going to change with manifold pressure. Now the fuel injector is designed so that the fuel pressure actually holds the injector closed. So the injector contains an electromagnet, or solenoid, which pulls the injector open against the fuel pressure. Now the force that the solenoid exerts is proportional to the amount of current through the solenoid, and therefore you need a certain amount of current to overcome a certain amount of fuel pressure to allow the injector to open. Now electrically, the solenoid has inductance because it's a coil of wire, and it also has resistance because it's not a superconductor. So the equation to define how it responds could be written as V equals L d I dt plus IR, right? L d I dt being the inductive part and IR being the resistive part. Now, if you're not all that familiar with differential equations, then you might still be able to look at that and see that the injector current depends on the voltage that's applied to it. So if you've got a higher battery voltage, then you will end up with a higher current through the injector. And also, a part that might be a little bit less obvious is that the higher the voltage, the higher the dIdt, which is how fast the current increases. So in other words, with a high battery voltage, the current through the injector will increase at a higher rate, so faster, than with a lower battery voltage, as well as the fact that the eventual current flowing through the injector will be higher as well, not including any current control done by an ECU. Now the other thing is that at higher fuel pressures, there's more force holding the injector shut, so you actually need a higher current through the injector to be able to open it. So what that means is that the amount of time that it takes before the injector has enough force to open against the fuel pressure that's holding it shut depends on the voltage. So a lot higher voltages mean less time, and also it depends on fuel pressure. Higher pressures mean more time. So this is an example response that we've measured with our injector tester of a fairly common aftermarket injector, which is a Siemens. They call it 220 pounds per hour, which I'll talk about my issues with that unit selection later on, taken at 3 bar of fuel pressure. Now this graph in theory should be a straight line that starts at the amount of time when the injector takes to open, and it goes up in a straight line. The slope of that line is the fuel flow rate of the injector. Now in practice we've actually got several lines here, and this is because each line corresponds to a different supply voltage. So we've measured it every volt from 7 volts up to 16 volts. And you can see that the higher voltages make the injector open earlier, and also it should be fairly obvious that once the injector's open, the flow rate is pretty much the same, that is, all the lines are parallel. Now if you have sharp eyes, you should also be able to see that below about 25 microliters of fuel being delivered, the curve has a bit of a kink to it. Now this is because of pintle bounce. You only see this on underdamped injectors, so overdamped injectors like the ID2000s and so on don't exhibit this kink in the curve at all. But what it means is that if you're trying to deliver less than about 25 microliters of fuel, that's going to be very hard to achieve with this particular injector. And this is what happens when people say your injectors are too big to get decent idle or whatever. Now also, for every injector at any given fuel pressure, there's a minimum voltage that needs to be applied to the injector for it to be able to open. Now we find in testing some injectors that some of them won't open at 5 bar pressure at a low voltage, like say 7 or 8 volt. I've even seen some injectors that won't open reliably at 4 bar pressure with 9 volts. So, and you might be asking the question, well, who cares? You know, I know I've got a decent charging system on my car, it's going to get 14 volts, what's the issue? And the issue is that when the car's cranking, you might only have 9 volts delivered to the injector. And if you've got a modern OEM system with 4 bar of fuel pressure, then you need an injector which is powerful enough to open against that with whatever voltage is available during cranking. Sometimes people do this, or the worst one is when people convert a car to high impedance injectors and don't short out the resistor pack that was in the car originally when it had low impedance injectors, and then they wonder why it doesn't why they don't open at the low voltages. It's because there's just not enough current there to open. But often it's not correctly diagnosed, and people will say things like, well, it's hard to start. If I try to start it, it doesn't start, but then on the second attempt it starts every time. What do I need to do to change in my cranking map to make it work? And actually what's happening is, during the time when they're cranking, the battery voltage is quite low. It's not enough for the injector to open, so they're not actually getting any fuel delivered in that time at all. When they take their finger off the key though, and it goes back to the on position, the voltage now increases up to say 12 volts or something like that. As the engine is still spinning down, it hasn't completely stopped yet, the ECU is still tracking the engine rotation, still pulsing in fuel, and at 12 volts now it actually can deliver some fuel. So then when they go to start it after that, some fuel's in there, it fires up and everyone's happy. But it's important to diagnose the problem correctly, otherwise you'll be chasing, cranking fuel maps and wondering why you're not getting anywhere. Now, in the calculation of fuel mass to milliseconds, the first thing we need to understand is that fuel injectors are really volume delivery devices. That is, as you change their temperature, the amount of fuel volume that they deliver does not change all that much. The mass does change though, because the density of the fuel changes with fuel temperature. The first thing that we need to do as an ECU is, when we've got fuel mass, is we need to convert that to fuel volume. So we need to know the density of the fuel to do that. Now, the ECU calculates this based on its knowledge of the stoichiometric ratio of the fuel, and also, if you've enabled it, the fuel temperature. So this is under the outputs fuel system. There's selection there for trim for fuel density. And if that's turned on, then the ECU will consider the fuel temperature when working out the fuel density. And you can see the density calculated under intermediate calculated values in the gauges window. Now, from knowing the mass and the density, the ECU can now work out the volume of fuel that needs to be delivered. Now, this volume is split between the different stages of the engine if you've got a staged injection engine, according to the algorithm which I described when I was talking about the fuel staging. And then once we've got the volume for each injector, we convert that into millisecond duration. And this is done as follows. So first of all, there's a minimum fuel volume setting that you can enable. And so in our previous example, we said that the injector wouldn't reliably deliver less than 25 microliters of fuel. If you set the minimum fuel volume to 25 microliters and the ECU is trying to deliver 10, for example, then it'll say, well, we know that we can't deliver 10 reliably, we'll just deliver 25, and it means that the engine's going to be too rich in that part of the map, but it's better than having the injector sometimes not open or spit and, cause bad misfires and that sort of thing. Now, secondly, the ECU calculates the effective on time based on the known fuel flow rate of the injector in cc's per minute, which is up from the fuel injector settings, which I'll explain in a second, and the volume need to be delivered. So from that we can work out the milliseconds. Now, for those who prefer to think in effective milliseconds rather than fuel volume, you can set a minimum effective milliseconds rather than a minimum fuel volume if you want to. The only thing I'd say is don't set both of those, because one of them is always going to happen before the other one. If you're going to use one, then set the other one to 0 so you don't get confused. Now next, the ECU has a 3D table of offset, or dead time if you like, which is the x-intercept on that injector graph I showed you before, which is a function of battery voltage and fuel pressure. Now note again, this is a differential fuel pressure, so this is the pressure across the injector. And this can be determined in two ways. The first way is to measure it directly. So for this you'll need a fuel pressure sensor, and the ECU will subtract the manifold pressure from the fuel pressure to work out the differential pressure. And the ECU then uses this to look up the fuel flow rate from the flow rate table, and also the injector dead time as well. And the second way is to use a nominal figure that you enter. So you do this if you're not using a fuel pressure sensor at all. Now for this there are two ways of doing it. One of them is to have a manifold referenced regulator where you'd enter value for the differential fuel pressure, and the ECU assumes that to be a constant. The other way is if you have a fixed pressure regulator, or the fuel gauge pressure I should say, does not change with manifold pressure, and in that case the ECU subtracts the manifold gauge pressure from the fuel gauge pressure that you enter to work out the differential pressure. And again, the ECU can use this to look up the fuel flow rate and the injector dead time. Now, the fuel flow rate and the injector dead time are tables which you can manually enter if you have the equipment and expertise to characterize injectors, or you can select from one of our predefined injectors that we've already measured. I need to give a big thank you to Paul Yor from Injector Dynamics for all his help with teaching me how to characterize injectors. It's been very helpful. Thank you very much. Now, if you select a predefined injector for which we have short pulse width compensation, which is the Injector Dynamics injectors, then that will be handled by the ECU automatically. Now, note that just like before I said you can look at the fuel density in the intermediate calculated values section in the gauge window, you can also look at the current flow rate and offset that the ECU is using as part of the fuel injector calculation. Now, one last point I'll say, which is I think it's a trick missed by a lot of tuners, which is that watching differential fuel pressure is actually really instructive. I've seen tuners try to diagnose fuel pressure systems by running external gauges and that sort of thing, and watch it as an engine comes on boost, and then manually subtract the boost pressure from the fuel pressure that they're seeing to try and work out what's happening. A really easy way to do it is just to put a fuel pressure sensor on the engine, wire it into the ECU, and monitor. There's a variable in the main variables called differential fuel pressure. Monitor that. If it's a decent fuel pressure regulator, like a Turbosmart FPR 800 or 2000, that does not change all that much. And if it changes more than about 10 kPa or 1 psi, then you know that you've probably got a fuel system problem. And in several occasions where I've been helping set up ECUs for customers, make sure everything's set up right and that sort of thing, get on the dyno and try and put a starting map into it and notice that the fuel pressure's all over the place. In every situation where that's happened, they've swapped the regulator out and it's been perfect when they put in a brand new FPR 800 on it. So just imagine how much time the tuners would have spent trying to get good maps into the ECU and complaining about inconsistency of lambda and so on if that information wasn't there. When the information's there, it's a very quick diagnosis to do, especially because fuel pressure makes such a big difference to the amount of fuel that actually gets delivered. And I'm going to quote someone, I don't remember who it was, I think it was an American like Shane Tecklenburg or Greg Banish or Paul Ure or someone, but they said, if you don't have data, then all you have is an opinion. And that's what I'll leave you with. Thank you very much.